right? Assume there are 2 point masses, m1, m2, separated by a distance x. Can one of you quickly tell me what is the potential energy of this system? Gravitational potential energy. 2 point masses separated by a distance x. How much is the gravitational potential energy?
Minus G m1 m2 by x.
Correct. Minus g m1 m2 by x. Fine. Now, we derived this result by first deriving work done by gravitational force between 2 point masses, and then we assumed at infinite separation the potential energy is zero. Then at finite separation we got this result. Okay. Now in the second case here, you assume this is a hollow sphere, uniform hollow sphere. Assume its mass is m1. Okay. The other mass is m2, and clearly the other mass is outside the hollow sphere. Now assume m2, the particle m2, is brought from infinity to this distance. It is always outside the sphere. Once the other particle, or when the other particle is outside the sphere, can one of you tell me the formula for force between the sphere and the point mass? How do you calculate force exerted by a sphere, uniform sphere, on a mass which is outside the sphere? What does the sphere behave like?
Sir, point mass.
Point mass placed at its center. Okay. For positions which are outside the sphere, if you want to find out the gravitational field or the gravitational force, okay, you can treat the sphere as a single particle placed at its center. So you can assume all the m1 is here itself, and let's say this distance is x. Now the force between the sphere and this particle is identical to the force between this particle and this particle. Now if the forces are identical, the work done in bringing the particle from infinity to this position will be same in both cases. And if work done is same in both cases, the potential energy will be same in both cases. Therefore, the gravitational potential energy between the hollow sphere and the particle m2 which is outside it can also be written as minus g m1 m2 by x. Is this logic clear to all of you? Any doubts in this? Okay. One of you tell me, will the situation be same even if it is a solid sphere or not? Aishwarya, what do you say? Had it been a solid sphere, uniform solid sphere, and m2 is outside, will you get the same expression for potential energy or not?
Sir, yes, sir.
It will be the same because once the position is outside the sphere, a solid sphere also behaves like a point mass placed at its center itself. Okay, so irrespective of whether it's a hollow sphere or a solid sphere, when the other mass is outside the sphere, you can treat the sphere as a single particle placed at its center. But remember, all this is valid for uniformly distributed spheres. If they are non-uniform, we cannot say. Okay, towards the end of the chapter, we'll solve such questions also. But for now, we'll assume spheres are uniform. Okay, so what we have here is a formula for potential energy between a sphere and a particle outside it. Okay, therefore, this formula, potential energy is minus g m1 m2 by x, can be used for, or can be used to find out potential energy between point masses. Okay, sphere and a point mass. You can use it between spheres also, but you should ensure that the point mass is outside the sphere. Then you can use this. Okay, on or outside, you can use this formula, right? Now consider a situation like this. Suppose you want to find out the gravitational potential energy between a hollow sphere. Okay, let's consider it as a uniform hollow sphere. Assume its mass is capital M and its radius is capital R. Okay. See, spheres, why we put so much emphasis on them is because ultimately we want to apply these concepts of gravitation to planets. Planets are spherical in shape, but they are not hollow spheres, they are solid spheres. Okay, almost spherical in shape and they are solid spheres. But a solid sphere is a collection of hollow spheres. Okay, so you should know the behavior of hollow spheres and solid spheres as well. So suppose there's a uniform hollow sphere of mass m radius r. Let's say there is some particle, a point mass, placed exactly at its center. Okay, and let that mass be small m. So sphere's mass is capital M. This particle's mass is small m. It is exactly at the center of the sphere. Okay. So these are two objects which have masses. Definitely there will be a gravitational potential energy, some amount of gravitational potential energy between them. But the problem here is that the particle M is inside the hollow sphere. Now we have to find out the potential energy between these two. Outside the hollow sphere, the sphere could have been considered as a point mass and you could have gotten the answer. Inside, how does it behave is what we are trying to find out. Okay. Any idea, anyone? How can we find out the potential energy, the gravitational potential energy between the hollow sphere, which is a bubble, and the particle inside? Any ideas? Think about it. I'll give you a minute. Any ideas, anyone? Okay. See, any quantity that you want to derive, be it force or field or potential energy, in any other chapter also, be it center of mass, moment of inertia, okay? You either break the system into smaller elements for which the formula is known to you. Otherwise, you use the fundamentals. Okay. Now we want to find out the gravitational potential energy between the hollow sphere and the particle placed at its center. Now, if you want to break the hollow sphere into smaller elements, the only elements in which you can break it are rings or point masses. Now we don't know the formula for potential energy between a ring and a particle yet. We didn't derive that. Even if we know, it will be very difficult because if you think of this hollow sphere as a collection of rings, one ring here, it will have some radius of its own. It will be at some distance from this particle. Another ring here will have some other radius of its own and it will be at some other distance from this particle. It will become too complicated an integration to do. Okay. So we can't consider, I mean, it can be done, but it's very lengthy. It's not useful here. So it's no use considering this hollow sphere as a collection of rings. Then the only option you are left with is to consider it as a collection of point masses. One point mass here, one point mass here, one here. On your screen, it may look like a circle. You have to visualize it in 3D. Okay. So the hollow sphere is a collection of infinite point masses like this. And we know the formula for potential energy between 2 point masses. That's all. So let's consider an element dm of the d capital M of the hollow sphere. Okay, total mass of the hollow sphere is capital M. So element mass will be d capital M. Quickly tell me, what is the distance between the particle at the center and the particle on the surface of the hollow sphere? Radius, capital R. Okay. Now these two particles will have some gravitational potential energy between them. Since one particle is an element of this sphere dm, they'll only have a small amount of potential energy between them. Okay. We know that gravitational potential energy between point masses is given by the formula minus g m1 m2 by x, where m1 m2 are the point masses and x is the distance between them. So between dm and m, the gravitational potential energy will be minus g m d capital M. Okay, small m is different, capital M is different. divided by the distance between them is r. Now every element of the hollow sphere will be at the same distance from its center. So all the elements will have the same amount of potential energy. Therefore, the total potential energy between the hollow sphere and the point mass at its center will be an integration of du. That becomes minus g small m by r. These are constants. Integral d capital M. D capital M was the mass of an element of the sphere. You integrate that, you get the total mass of the sphere. Therefore, potential energy in this case becomes minus g capital M small m divided by the radius r. Simple logic. All the mass of the sphere, capital M, is at the same distance from small m. And potential energy depends on mass and distance between them only. So since all the masses are at the same distance, you can directly use the formula minus gmm by r. But this is valid only when the particle is at the center of the hollow sphere. Okay, let's consider another case now where the particle is not exactly at the center. We'll see what to do. So between a hollow sphere and a particle which is exactly at its center, the potential energy is minus gmm by r. Okay. Suppose you move the particle away from that position. Let's say it is at a random position which is at a distance x from the center of the hollow sphere. We need to find out the potential energy between the mass of the hollow sphere and this particle which is inside. Now, there's no use considering the hollow sphere as a collection of rings. If you treat it as a collection of point masses also, this time it becomes difficult. Why? Because every point mass will not be, all point masses will not be at the same distance. That distance becomes variable and it's too complicated to write an expression for that distance and integrate. Okay. So breaking it down into rings won't work. Treating it as a collection of point masses also is not going to work. Can any of you come up with an idea to find out the potential energy in this case? Potential energy between the hollow sphere and that particle. Think about it. I'll give you a minute. Any ideas, anyone? Okay, no problem. See, treating it as collection of rings doesn't work. Treating it as collection of point masses also doesn't work in this case. Then there is something more fundamental we can use. We know from basics that the change in potential energy when you go from when a mass is taken from one position to another position, or even more generally speaking, the change in potential energy when the arrangement of a system is changed is negative of work done by conservative forces, right? You can use this. Okay. But using this, you get change in potential energy, which is potential energy at final arrangement minus potential energy at the initial arrangement is negative of work done by conservative forces. So if you know potential energy at one position, then you can tell potential energy at another position using this basic formula. And that much we know. When the particle is exactly at the center, we know its potential energy. So assume the particle is taken from this position to this position. In that process, we can find out work done. And if we can find out work done, we can tell the final potential energy. Okay. See, keep these ideas in mind. It's okay that you didn't get this thought, but from now onwards, you should confidently say that maybe we can do it like this. Okay. Since those other methods are not working, then you will have to rely on the basics only. Okay. So assume the particle is taken from the center of the hollow sphere to a distance x away from the center. Initial position is the center. At the center, we already know its gravitational potential energy minus g capital M small m divided by the radius. Okay, center has an advantage, it is equidistant from every element on the sphere. So we could easily find out the potential energy when particle is at the center. Okay. Now, if you want potential energy at a distance x away from the center, you need to know what is the work done by gravitational force. Okay. Now, gravitational force between what and what? Between the hollow sphere and this particle. Force of gravitation between the hollow sphere and this particle can be calculated as mass of the particle multiplied with field of the hollow sphere. Okay, this is what we make use of. I mean, this is what fields are meant for, to find out force. Okay, one of you recollect and tell me how much is the gravitational field created by a hollow sphere inside itself. We didn't derive this, but I gave you a direct result. How
Zero.
much? Good, zero. Okay. Now that particle is being taken from the center of the hollow sphere to another point inside the hollow sphere itself, to another position inside the hollow sphere itself. So as it is taken from A to B, it does not experience any field from the hollow sphere. This is zero. That means it does not experience any force at all. And if it does not experience any force, that means gravitational force doesn't do any work at all as the particle is taken from A to B inside the hollow sphere. And if gravitational force isn't doing any work, the potential energy does not change. Okay. Therefore, how much ever is the potential energy at the center of the hollow sphere, okay, when particle is at the center of the hollow sphere, same will be the potential energy even if it is placed anywhere else inside the hollow sphere. Okay, very useful result. And see, these same results we'll be using in the first chapter of 12th class, electrostatics or electric charges and fields. Okay, first, second chapter, very important ideas these are. Okay, therefore, potential energy between the hollow sphere and this particle, when the particle is anywhere inside the hollow sphere, is always the same, and it is minus g capital M small m divided by the radius r. Okay, there's no field inside a uniform hollow sphere. The hollow sphere does not create a field, so the particle inside it doesn't experience a force from the hollow sphere. And if it doesn't experience a force, no work will be done, no change in potential energy. So whatever is the potential energy at the center, anywhere inside the hollow sphere till the surface, it will have the same potential energy. Okay, keep this point in mind. So when the particle is outside the hollow sphere, you treat the hollow sphere as a point mass and use the point mass formula for potential energy. When particle is inside the hollow sphere, the potential energy is independent of where the particle is placed. It's always the same. Okay, it's not zero, but it's always the same. The field is zero. Potential energy will be there. Potential energy is zero only at infinite separation. Okay. Note down this result, all of you. Anywhere inside the hollow sphere, the potential energy is minus gmm by r. Next, potential energy between a solid sphere and a particle inside. Okay. Assume this is the solid sphere. Obviously, when you look at it from one side, it looks like a circle. Disk, it looks like a disk, but it's a sphere. Okay. Let's say the solid sphere's mass is capital M, radius is r. Now, when you are, okay, not when you are, when the particle is outside the solid sphere, at a certain distance from its center, you know that you can treat the solid sphere as a single particle, and the formula will be the point mass formula, minus g m1 m2 by x, or minus g capital M small m by x. That's fine. Up to surface also that is valid. Okay. When the particle is exactly on the surface of the solid sphere, you can say the potential energy between them is minus g capital M small m by radius r, because the distance from the center is the radius. That is valid. But how to calculate potential energy when the particle is inside the solid sphere? Let's take the particle to the center of the solid sphere. Let's see if it helps. Okay. Now, in case of a hollow sphere, the center had an advantage. What advantage? Every particle of the hollow sphere, every element of the hollow sphere was at the same distance. But in case of solid sphere, that advantage is gone, because different elements of the solid sphere will be at different distances from the center. So finding out potential energy when particle is at the center is not easy. But there's a way to do it. Okay. Can any of you tell me an idea how to find out potential energy between the solid sphere and the particle which is kept at its center? The particle is actually a point mass. Just for us to be able to visualize, I'm showing it as a thick dot. Okay.
We can consider the solid sphere as a collection of hollow spheres.
That's all. Correct. You can treat the solid sphere as a collection of hollow spheres. And we know the formula for potential energy between a hollow sphere and a particle placed at its center. So for hollow sphere, if you know the formula, solid sphere can be done. But is there any advantage? You will do all that integration by treating it as hollow spheres. You will do all that integration and find out the potential energy at the center. Okay. But when you take it away from the center, take it to some position here, solid sphere creates a gravitational field inside it. Okay, we had discussed this 2 classes back. We derived it actually. Using hollow sphere result, we derived solid sphere result. Okay, do any of you remember? Okay, it's here on the screen anyway. The gravitational field inside a solid sphere is not zero. It is gmx divided by r cube. Field is there and it's a variable field also, not even a constant or uniform field. Okay. Now, so what if there is a field? If there is a field, when you take the particle from position A to position B, work will be done on it. And if work is done, you will have another formula for final potential energy. Center potential energy will not be the same as potential energy anywhere else. Okay. Our aim is to find out potential energy at a random distance x. So one way to do it is treat it as a collection of hollow spheres. I mean, there are many ways. I'll tell you the different approaches that you can take. Treat the solid sphere as a collection of hollow spheres. Okay. Find out potential energy when it is at position A. That is one way to do it. Find out potential energy at A. Then you find out work done when it is taken from A to B. And then you get potential energy at B. But this is like two problems in there are like two problems in this. Finding out potential energy at A requires integration. Work done as it is taken from A to B also requires integration. Why? Because the field is a variable field, non-uniform field. Force will be non-uniform. Work done will require integration. Can be done this way, but it is lengthy. Next. Our ultimate aim is to find out the potential energy at B, not at the center. Okay, at random position, if you know, then center also you can write. You just substitute x as 0, you'll get center value. So the next approach you can take is directly by treating it as a collection of hollow spheres, get the potential at B. But there's a problem here. For some hollow spheres, B is an external point, and for some hollow spheres, B is an internal point. The formula for potential energy of a hollow sphere for a particle which is outside it is different, and for a particle which is inside it is different. So it can be done this way. We can treat it as a collection of hollow spheres like this. Okay. And find out potential energy. But again, from 0 to x, you will have to do one kind of integration. From x to the radius capital R, you will have to do another kind of integration. Okay. The spheres whose radii are from 0 to x For those spheres, this particle is outside. You'll use one formula for potential energy. For spheres whose radii are between x and capital R, for those shells, hollow spheres, this particle is inside. You'll have to use a different formula for potential energy and integrate. So slightly complicated, but can be done. Okay. Those of you who have time, practice those approaches also. Okay, I'll give you some hints. So the second approach is to treat it as a collection of shells and integrate. There's another approach also. We know the potential energy when the particle is on the surface of the solid sphere. So you can integrate from surface, okay, by assuming it is displaced from the surface to this position B, which is at a distance x from the center. How does this help us? This helps us because we already know the formula for potential energy on the surface. So potential energy at A is known to us. All you have to do is find out work done as it is taken from A to B. And from that, you can tell potential energy at B. So out of these three methods, this third one is the easier approach to take. Fine. And that is what we are going to do. This particle's mass is small m, and assume small m is taken from the surface of the solid sphere to a distance x from its center, where x is inside or less than the radius of the solid sphere. Okay. Is the idea clear to all of you? Or are all three ideas clear to all of you? If you have any doubts, you can ask. Okay. So assume the particle was exactly on the surface initially. Therefore, potential energy at A, that is the initial potential energy of the particle. Can one of you quickly tell me? Vanilla, don't answer. Others, any one of you. What's the potential energy between a solid sphere of mass capital M and a particle of mass small m, which is just on its surface?
Sir, is it minus G M M by R? Like
Correct.
capital.
Correct. Minus gmm by capital R. The particle is just outside the sphere. So the sphere can be considered as a point mass. So you can assume all the capital M to be here and all the small m is at a distance R from it. So the initial potential energy becomes minus G capital M small m by R. Correct. Okay. Now we need final potential energy. If you can get the change in potential energy first, then since you know initial potential energy, you will be able to tell what is the final potential. And how do you get change in potential energy? Negative of work done by gravitational force. Okay. Let us work on this. As the particle is taken from position A to position, now some of you may be wondering, sir, how can we take it inside a solid sphere? It's completely filled with mass. Okay. Assume there is a very, very narrow tunnel made. Okay. As I told you, the particle's dimensions are negligible. It's a point mass. Practically speaking, I mean, actually speaking, you won't be able to see it. For us to be able to visualize, we have considered a large point mass just for us to be able to see it. Okay. It's actually a very small point mass. You can assume whereas there's a very narrow tunnel, okay, dug along the diameter to the center, and the particle is being taken in that tunnel. So the sphere's mass is not disturbed effectively. It's almost the same, right? That way. So imagine the particle being taken from A to B. As the particle is taken from A to B, the sphere will be exerting a gravitational force on it. How much? The gravitational force exerted by a sphere can be calculated as field multiplied with the mass. So force is equal to mass multiplied with the field. The mass is small m. Field is created by the solid sphere. Solid sphere's field inside it is given by this formula, gmx divided by r cube, where x is the random distance from the center. Okay, just to avoid confusion, let's call this inside distance as A. We want to know the potential energy when the particle is at a distance A from the center. Now, as the particle is taken from surface to this position, from A to B, at different points or at different instants, it will be at different distances from the center. That distance is what you call as x in this formula. So x is a variable now. And what are the limits for x? Initially it is capital R, the radius. Finally, it reduces to small a, the distance where you want the field. So x varies from, in our integration, x will be varying from radius to the point A, the distance A. Okay. We have an expression for force and we know the force is going to be variable. So how do you calculate work done? Integral f dot ds. And listen to this very carefully. Integral f dot ds becomes integral magnitude of the force. Okay, I'll have to write it this way. Magnitude of the displacement, cos of the angle between them. Okay. A solid sphere always creates a field towards its center. So if you visualize the field produced by the solid sphere, it will be like this, towards the center. Okay, if field is towards the center, the force will also be towards the center. Fine. Let me just take another picture. This is the center. Let's say as the particle is being brought from the surface to some random distance a, assume at some instant it is here. Then the force acting on the particle, the gravitational force acting on the particle will be towards the center of the sphere, solid sphere. And that force can be written as mass multiplied with the field. Okay, so that's the direction of the force. And we know the direction of displacement is also towards the center only, no? From surface, we are bringing it in. So displacement ds bar is also towards the center itself. Therefore, what's the angle between force and displacement? 0 degrees. As it is being taken from where to where? From this initial position A to some final position B here. As it is being taken, at any instant, the force and displacement will be in the same direction. Okay. Now, we know the field magnitude. Multiply with mass, you will get the force magnitude. So force magnitude is known to us. Let's write it as it is. G, capital M, small m, x divided by r cube. That's the magnitude of force. We next have to multiply it with the magnitude of displacement. Now x here is a variable. So integration can be done, or it will be possible to integrate only if you express the displacement in terms of dx. Okay. What is x? X is the distance from the center to the position of the particle at any instant. That is what we are calling as x. So can one of you tell me how displacement ds can be related to change in x dx? How to relate ds to dx? Are they equal, or is there any adjustment to be made? Think carefully and answer. Okay. And I got one answer as ds is negative of dx. Okay, very good, very good. See, we are moving towards the center itself. And by whatever distance the particle moves towards the center, by that much x will decrease. Okay. So magnitude wise, ds and dx are same. But x is a decreasing quantity. X is a decreasing quantity means dx is negative. Okay. We want to relate magnitude of displacement ds to dx. Now you know dx is going to be a negative term. Then you can't say magnitude of displacement is dx itself. Why? Magnitude of a vector can never be negative, but dx is negative. So if you want to write magnitude of displacement in terms of dx, you write it as minus dx. Okay, since x is a decreasing quantity, dx is going to be negative, minus dx will be positive, and that can be taken as magnitude of displacement. Okay, that's why we include a minus sign here. Next, cos theta. We know the angle between force and displacement is always 0. Cos 0 is 1. This integration has to be done with limits r to a, because initially the mass was at a distance r, x is equal to r. Finally, it is taken to x is equal to a. Okay. And what will this integration give us? It will give us the work done by gravitational force. That we will relate to potential energy and find out the final potential energy. Okay. Keeping the constants outside, minus g capital M small m divided by r cube. Put all of them outside. You will be left with integral x dx. Limits r to a. Integral x dx is x square by 2. Again, limits r to a. It becomes a square by 2 minus r square by 2. So work done turns out to be minus gmm by the 2 also I'll keep outside, 2r into a square minus r square. And this is work done by what? Work done by the gravitational force. And we know work done by gravitational force will be negative of change in potential energy. So you can remove this minus and take the rest of the equation as change in potential energy. Okay, we are getting somewhere. Therefore, delta U, that is potential energy at a distance a, the final distance was a, minus potential energy at the initial distance. Initial distance, it was on the surface, is equal to gmm by 2r into a square minus r square. Okay. And we know the potential energy on the surface. Therefore, we can tell potential energy at a distance a. Surface potential energy was minus g mm by capital R. Minus minus cancel. Left hand side it will be plus, but when it goes to right hand side, it will again become minus. Therefore, potential energy at a distance a from the center inside the solid sphere will be, I'll split that right hand side into two terms, gmm a square by 2r minus gmm. Okay, wait. How did it become r in the denominator? It is r cube in the denominator. Small mistake. Okay, gmm a square by 2r cube minus gmm r square by 2r cube becomes 2r. Okay, and then this term that is there plus gmm by r on the left hand side becomes minus gmm by r on the right hand side. Okay, put this all together. Potential energy at a distance a, or you can call it potential energy at a distance x from the center inside, becomes minus 1 by 2 minus 1 is minus 3 by 2 gmm by r plus gmm a square by 2r cube. Complicated expression, and quite possible that you won't remember it till your final exam. Even if you remember in the final exam, most likely you can't recollect it as it is. You may forget this minus sign, or you may take two minuses. The whole solution will go wrong. So there's no point remembering this formula anyway. But practice the derivation. You should be able to derive this within 30 seconds. Okay, you can do it also. It's no big deal. Okay. Surface we know minus gmm by capital R. Take it from surface to wherever you want to know the potential energy. Derive the expression for work done properly with limits. Final potential energy you will get. Okay. So this is the formula for potential energy between a uniform solid sphere and a particle inside it. Okay, inside it. If the particle is outside, you will use the point mass formula itself. You don't need this expression at all. If the particle is inside, you will need this. Okay, and we took the distance as x, no? So I'm not writing a square, I'm writing it as x square. Okay. Now using this formula, you can tell what is the potential energy when the particle is at the center of the sphere also. When you go to the center of the sphere, x becomes 0. And if x is 0, that whole term is 0. Therefore, potential energy when small m is at the center is minus 3 gmm by 2r. Okay. Now we had one idea to get potential energy at the center by treating it as a collection of shells. Even if you do it that way, you will get the same answer. And you need to do it that way also. Only then your problem solving skills will improve. Okay. See, this derivation I have done. You have seen. You have to put your own ideas also. No? You have to put your own efforts also. Only then your ability to solve problems will improve. Okay. So yeah, yesterday I didn't send the worksheet, but tomorrow I will. And in that worksheet, you'll derive this same result in a different manner, okay, by treating it as a collection of shells. You will have to give some time to it. Otherwise, you are, as I said, speed won't improve, your application won't improve. Just listening to the class is never enough. Okay. So what we have done so far in today's class is derived the gravitational potential energy between a hollow sphere and a particle inside it, and also a solid sphere and a particle inside it. Okay. Now, if you know potential energy, what is the use? You can use it in energy conservation based questions and find out speeds and such things. Right. Okay. So far what we have discussed are the basics of gravitational force. What is the expression for gravitational force between point masses? Then how to find out between extended system and a point mass. We did that rod and particle question. Then we considered ring. Okay. Then we talked about field actually. We discussed what is gravitational field. We made use of gravitational field to find out force between ring and particle. Then we talked about gravitational field produced by a hollow sphere inside, outside, solid sphere inside, outside. Field helps you in calculating the force. Okay, so we talked about force, field. After that, we discussed work and potential energy. We know potential energy between point masses. Now we know potential energy between spheres and point masses also. Okay. Let us apply all this to a planet and mass system from now on. Okay. First, gravity of a planet. Consider the Earth itself to begin with. Just a moment. Planets, unless otherwise specified, will be considered as solid spheres, that to uniform solid spheres. We know that the Earth is not made of the same material everywhere. Okay, it's not a uniform solid sphere, but assume it is. Okay. Let's say the planet's mass is capital M, radius is r. They can ask you questions based on non-uniform solid spheres also. Okay. How they will ask? They'll tell you that the material or the density varies from distance to distance. At one distance, there is one density, at another distance, another density. Actually, in the Earth, it's like this only, no? The core of the Earth is made of some material. The surface of the Earth is made of some other material. So as you move away from the center, the material changes. That is where the hollow sphere ideas will work. If density is varying from distance to distance from the center, density is varying from radius to radius, then at one particular radius, you will consider a hollow sphere. You will find out what is the gravity of that one hollow sphere and you will integrate to get the gravity of the entire planet. Okay, we'll come to such questions. For now, let's assume it's a uniform solid sphere. Okay. Suppose there's a particle placed on the surface of this planet. Exactly here. It's a very small mass, as I said. For our visualization, I'm showing it as a significantly large mass. Okay. Assume its mass is small m. Let's say it's exactly at the surface. One of you quickly tell me, what is the gravitational force, or how much is the gravitational force between this planet and this particle? You can see that the particle is just outside the sphere. Okay. So how much will be the gravitational force between them? Rishi?
Minus g m by R.
Minus
Same
gmm
thing.
by r is the formula for potential energy. I asked you gravitational force. Aishwarya.
So Gmm x by r cube.
See, gmm x by r cube is the formula for force when the particle is inside the solid sphere. This one is just on the surface of the solid sphere. It's outside actually. Anyone?
So gmm by r square.
Simple. Okay, the point mass formula you'll use. G capital M small m divided by the square of distance between them, r square. On the sphere or outside the sphere can be treated as a point mass placed at its center. Okay, so these two are at a distance capital R from each other. So the force will be G capital M small m by r square. Okay. Now if this is the force, on whom is this force acting? This force is acting on small m. Of course, it acts on the earth also. Fine. On small m, this much force will be acting. And if this is the force, then you can equate this to, okay, G capital M small m by r square. Now, generally we write force is mass into acceleration. Actually, just a moment. Actually, it is net force is mass into acceleration. Okay, there could be other forces also acting on this particle. We know the gravitational force acting on it is this much. Then you can equate this to mass into acceleration due to gravity. That is what we call as small g. That is what we denote as small g. Now, where is this particle present? Exactly on the surface of the planet. So this acceleration is going to be acceleration due to gravity on the surface of the planet, which we will denote by the symbol g naught. And then you cancel small m. You therefore get g naught, acceleration due to gravity on the surface of a uniform planet, as g capital M divided by r square. It doesn't depend on small m. And we know that we have always been solving problems by taking g as 9.8 or 10 meter per second square, irrespective of the object. Okay. So this is proof that acceleration due to gravity doesn't depend on the object. It depends on the planet which is creating this. Okay. Capital M here is mass of the planet. Capital R is the radius of the planet. Using this formula, you get the gravity exactly on the surface of planet. Now, G is 6.67 into 10 power minus 11. I asked you to take it as 20 by 3 while doing calculations. That is G in SI units. Mass of the earth is about 6 into 10 to the power of 24 kg divided by radius of earth 6,400 kilometers. So that becomes 6.4. 6,400 itself is 6.4 into 1000. Kilometer is 1000 meters. So it becomes 6.4 into 10 power 6 meters, and you have to square this. You do this calculation, you will see that gravity on the surface of earth will be close to or approximately 9.81 meters per second square. Okay, but this is the general formula using which you can estimate acceleration due to gravity on any planet, not just the earth. Okay, so the formula for acceleration due to gravity on the surface of a planet is gm by r square. M is the mass of the planet, r is the radius of the planet, and we have made an assumption here. We assume the planet to be uniform. Is this clear to all of you? Any doubts in this? Okay. Let's solve some problems based on this quickly. First, the mass of some other planet, okay, is 4 times the mass of Earth, and the radius of that other planet is okay, let's say the radius is also 4 times the radius of Earth. Then what is the acceleration due to gravity? Okay, how much is the acceleration due to gravity on that planet? Assume acceleration due to gravity on Earth, on the surface of Earth, is 10 meter per second square. Then how much will it be on the surface of that planet? Solve this quickly. I'll give you 2 minutes. Okay. So it's just an application of the formula that we just derived. Gravity, acceleration due to gravity on the surface of the planet just depends on mass of the planet and its radius. Okay. Therefore, acceleration due to gravity on the surface of this new planet or some other planet can be calculated as g, mass of that planet divided by radius of the planet squared. Now we don't know their exact values, but we know in terms of Earth values. G into mass of the planet is 4 times the mass of Earth divided by radius of planet is 4 times the radius of Earth. When you square it, it becomes 16 times Re square. 4 by 16 is 1 by 4. So it is 1/4 of G mass of Earth by radius of Earth squared. And G into mass of Earth by radius of Earth squared is gravity on Earth, which is 10. So the answer is 10 by 4, 2.5 meters per second square. Simple. Any doubts in this? Okay. Let's try a slightly different question. And questions like this are quite common in your final exams. Suppose there's another planet whose density, okay, density is denoted by the symbol rho. Density of the other planet, let's say, is 8 times the density of Earth. Okay. And the radius of the other planet is twice the radius of Earth. Find out gravity on the surface of that planet. Okay. Again, consider gravity on the surface of Earth as 10 meters per second square. So this time the mass ratio is not given. Instead, the density ratio is given. Okay. So all you have to do is think of the relation between mass and density, and then you can solve this. Do it all of you. I'll give you 3 minutes. Okay. Anyone other than Vanilla, can you tell me the relation between mass and density? General relation.
Density is equal to mass by volume.
So mass becomes density into volume. Fine. Now you need gravity on the surface of the planet, right? Gravity on the surface of a planet is g times mass of the planet divided by its radius squared. Now we know the ratio between radius of the planet and radius of Earth. We need their mass ratio. Okay. Mass of planet divided by mass of Earth would be mass is density into volume. So density of planet into volume of planet. Planet is a solid sphere. What's the volume of a sphere? 4 by 3 pi r cube. Okay, that's how we express the volume of a sphere. Divided by density of Earth into volume of Earth is also given by the same formula. That's all. So if you want the mass ratio, what is the density ratio given? 8 times. 4 by 3 pi will get cancelled. And radius ratio, radius of planet is 2 times the radius of Earth. 2 cube is 8. 8 and 8 and 8 becomes 64. So mass of planet is 64 times the mass of Earth. That's all. So gravity on the surface of the planet becomes g into 64 times the mass of Earth divided by radius of planet is 2 times radius of Earth, and you square it, it becomes 4 times the radius of Earth squared. 64 by 4 is 16 times. That's all. The answer is 16 GME by RE square. 16 into 10, 160 meters per second square. 10 times stronger gravity. Okay. Do any of you know how much is the gravity on the surface of Moon compared to that on the Earth? I'm sure you must have come across this in your lower classes. How much is the acceleration due to gravity on Moon compared to Earth?
Sir, I think moon gravity is 2, so it would be somewhere around 1 by 5th of the Earth.
It's 1/6 of the Earth. Okay. Fine. But I think you can do it quite easily. What I was going to ask is, we know the gravity on the surface of Moon, and we know Moon's mass is 1 by 100 times the mass of Earth, approximately. Or 1 by 90 times, whatever it is. Mass ratio is given, gravity ratio is given. I was going to ask you the radius of Moon. Can be done by using this same formula. Okay. So exactly on the surface of a planet, this is how you calculate acceleration due to gravity. But what if we move higher above the planet or deeper into the planet? Let's see. So second case, acceleration due to gravity at a height h above the surface of a planet. Okay, so this h is from the surface, not from the center. Okay. Now, okay, by now you must have realized, or let me just tell you this. See, we are deriving acceleration due to gravity, and acceleration due to gravity is the force of gravity divided by the mass that experiences the force. And force by mass is nothing but field. Okay, so acceleration due to gravity is nothing but gravitational field. So we can use that result directly. We don't have to find force divided by mass every time. Okay, let's take a position somewhere here outside the planet. And how far is it? It is at a distance h from the surface of the planet. Okay. If the distance is h from the surface of the planet, then all the way from the center of the planet, it will be r plus h. So you can take distance x is equal to r plus h. And one of you quickly tell me, how much is the gravitational field outside a solid sphere? Gravitational field produced by a solid sphere outside it. What is the
Sir,
formula?
minus G
Yeah,
M
minus comes for potential energy. I'm asking you field.
G M by R square.
Gmm by r square is the force. But why will you take r? R is the radius of the planet, no?
Okay. So GM by R plus H.
Okay, r plus h whole square you can write. Whole square. So basically the formula for field outside a hollow sphere or a solid sphere is G capital M divided by x square. Okay, it's like the field of a point mass only, Gm by x square. Okay, you need to solve more problems based on this only, then you will memorize. Fine. Here, gravitational field is nothing but acceleration due to gravity. So acceleration due to gravity outside the planet or at a certain height above the planet will become Gm by r plus h whole square. Therefore, as height increases, okay, h is in the h is in the denominator. As height increases, acceleration due to gravity decreases. And I'm sure you all know this. As you go to very large heights above the surface of planet, gravity becomes weaker and weaker. Okay. And we say that in space there is no gravity. It's not that there's no gravity. When you go too far from the surface of Earth, the gravity becomes negligible. Okay. It becomes zero only at infinity. You should not say there is no gravity. You should say there is negligible amount of gravity. But that also happens when you go to very large heights above the Earth, not small heights. Okay. We'll discuss all this in detail. You'll understand. So once you are outside the planet, this is the formula you are supposed to use to find out the acceleration due to. Now we are all outside Earth only. Okay. Even if we are standing on Earth, only some points of our feet will be in contact with the Earth, exactly on the surface. All other points of our body are outside the Earth only. Does that mean acceleration due to gravity is different for different points on our bodies or the objects that we see around us? No. Why? Radius of Earth. How much is it? 6,400 kilometers. Huge radius. Okay. Even if you add a small height to it, okay, the everyday heights that we come across, the value r plus h is still going to be approximately r itself. Okay. So for very small heights, very small heights that we come across in daily life, acceleration due to gravity will almost be gm by r square itself. That is 9.8 or 10 itself. That's what we have been using all this while. And that's what we will use after this chapter also. But just for you to understand when gravity significantly changes, we are discussing all this. For small heights on the Earth's surface or outside the Earth's surface, there won't be a significant change in acceleration due to gravity. It will still be approximately the same as the surface value. Okay. I'm talking about very small heights. Okay. The heights that we come across in daily life. What heights do we come across in daily life? Few meters. maybe few kilometers also, like 1 to 10 kilometers. Okay, there won't be a significant change in gravity. Okay, so all this while, like all the chapters that we discussed till now, we used to assume G to be uniform, 10 meter per second square, and we solved right from kinematics to system of particles. That is safe to do. Okay. But if you go to significant heights above the Earth's surface, then this is the formula for gravity, acceleration due to gravity. Fine. Now it is common practice to express this in terms of gravity on the surface. Gravity on the surface is G capital M by R square. Gravity at a height above the surface is given by this formula, Gm by R plus H whole square. What I'm going to do is take R common in the denominator, then it becomes 1 plus H by R and whole square. So this becomes Gm by R square. Okay. Gm by R square. And we'll be left with what? 1 plus H by R whole square in the denominator can be written as 1 plus H by R to the power minus 2 in the numerator. Simple mathematics. Why are we taking this pain? Because we would like to express gravity in terms of surface value, G naught. Therefore, gravity at a height will be gravity on the surface into 1 plus H by R to the power minus 2. There's literally no use of writing it this way because power minus 2, we don't know how to calculate. We are anyway going to send it to the denominator and do it. Okay. There's no use writing it this way at all. But there's something we can do here. If the height that you're talking about is very less compared to the radius. Very less means not these everyday heights like few meters and all. Few kilometers is what we are talking about, but significantly less than the radius. Now, when to consider this approximation to be valid? When the height is maybe less than 1/10 of the radius. How much is the radius of Earth? 6,400 kilometers. 1/10 of that will be 640 kilometers. So at heights less than 640 kilometers approximately, this assumption is valid. H is very small compared to R. Now, if H is very small compared to R, H by R will be very small compared to 1. Okay. You look at this expression. You have G naught into 1 plus H whole power minus 2. 1 plus H by R whole power minus 2. Call H by R as X. Okay, we have used the term X already as the distance from the center. Let's call it as A. So treat this as, okay, which part? Only this 1 plus H by R whole power minus 2. Treat it as 1 plus A whole power minus 2. Where in place of A you have H by R. In fact, treat it as 1 plus A whole power N. In place of A you have H by R. Sorry, in place of H by R you have A. And in place of minus 2 you have N. So N is minus 2. Okay, I'm just writing the equation in different terms. Now H by R is very small compared to 1. That means A is very small compared to 1. And if A is very small compared to 1, 1 plus A whole power N. Can any of you tell me what this can be approximated to? We used to do this in the beginning, especially those of you who were there in my differentiation classes, okay, calculus classes, we learned this approximation there. What is 1 plus X whole power N when X is very small?
So 1 plus A into N.
1 plus A into N. Good, good. It becomes 1 plus NA. Okay, this is a mathematically valid approximation. It's called binomial approximation. Okay. 1 plus A whole power N. If A is very small compared to 1, you can write it as 1 plus NA. We had used this in error analysis also. Anyway, that's fine. Even if you don't remember it, it's okay. But you have to revise at some point. Now, what is A in our derivation? H by R. And what is N in our derivation? Minus 2. Therefore, 1 plus H by R whole power minus 2 is approximately equal to 1 plus minus 2 times of H by R. That becomes 1 minus 2H by R. Okay. Then if 1 plus H by R whole power minus 2 can be written this way, gravity at a height can be written as gravity on the surface into 1 minus 2h by r. This way the equation is more usable. Directly substitute the height where you want gravity, you will get the answer. But remember, this is not always valid. This is only valid when h is very small compared to r. How small is very small? Less than 640 kilometers, but they'll give you that in the problem. Whether you are supposed to consider it as a small height or not, they'll give you. If you don't know whether the height they are talking about is small or very large, you will have to use the general formula, which is always valid. The formula which is always valid is this one. At any height, you can use this. Okay. But if the height is small compared to the radius of Earth, you can use this also. Both formulas will give you almost the same answer. Actually, whenever you learn something like this, no, like let's say some teacher told you that this and that will be same, you have to check on your own. Okay, don't trust anything that, I mean, it's not that don't trust, but anything that you are told, verify it. Okay, it will improve your calculation, it will improve your understanding. Okay, so I told you that if height is less than 1/10 of the radius, you can use this formula. So what you can do is take some height. Okay, let's say height above the surface of Earth as 1/20th of the radius. Substitute this in this formula and substitute this in the other formula also. What is the other formula? Gravity at a height is G capital M by R plus H whole square, or we wrote it as G naught into 1 plus H by R whole power minus 2. You can write a G naught by 1 plus H by R whole square. Substitute this H as R by 20 in this formula also. Then you will know if the answers are almost the same or not, and you will know whether this formula is actually correct or not. Of course, and when it's given in a textbook or when teacher says it will be correct only, but you check it once so that your understanding will improve. Do this later on your own and tell me whether you are getting the same results or not. So what we have discussed here is how to find out acceleration due to gravity at a certain height above the surface of a planet. If you are at a certain height above the surface of a planet, obviously you are outside the planet. And acceleration due to gravity is nothing but gravitational field. So you will be using the formula for gravitational field outside a solid sphere, gm by x square, where x is the distance from the center. So it becomes radius plus the height. Simple. That will give you the gravity. Okay. Solve one problem based on this. Gravity on the surface of a planet. G naught stands for gravity on the surface of a planet. Okay. Let's say is 20 meters per second square. Some random planet. Okay. Find out gravity at a height equal to the radius of the planet. We are going to a height which is equal to the radius of the planet. So at that height, how much is gravity? Solve this quickly. Okay, I got two answers as 5 meter per second square. Fine. Now gravity at a height equal to the radius of the planet. Now if height is equal to the radius, it's not a small height. It's not negligible, it's not small also. So you'll have to go for the actual formula, which is G naught divided by 1 plus H by R whole square. The G naught is gravity on the surface of the planet divided by 1 plus H is equal to radius. So H by R becomes 1 whole square. 1 plus 1 whole square is 2 square 4. 20 by 4 becomes 5 meters per second square. You could have solved it this way also. Gravity on the surface is gm by r square. Gravity at a height equal to r. If height is equal to r, that means distance from the center of the planet is 2r. Then the gravity there becomes gm by 2r whole square, which is 4r square. So effectively it is 1/4 of the surface value. That way also you could have said that it is 5 meters per second square. Okay, so this is about gravity at a certain height above the planet. And see, this was not a small height, this was not a negligible height, so we use the actual formula. Okay, which will always work. Okay, next case. Acceleration due to gravity inside a planet. At a depth small d from the surface. Okay, let's visualize this situation first. I'll treat the planet as a solid sphere, and not every planet is as colorful as the Earth. Okay, consider this to be a planet. What we now want is acceleration due to gravity at some point inside this planet. Okay, let's consider this as the point. The depth of the point from the surface is given to you as small d. From the surface, if the depth is small d, then from the center of the planet, obviously, the distance x will be r minus d. So what we are looking for is acceleration due to gravity at a distance r minus d from the center of the planet, center of the solid sphere. Why am I writing it like this? Because we have a formula for distance from the center. Okay, can one of you tell me how much is the gravitational field inside a solid sphere?
Gmx by r cube.
Gm x by r cube. Simple. Now in place of x you substitute r minus d, and gravitational field itself is acceleration due to gravity. Okay. Therefore, acceleration due to gravity at a certain depth will be Gm by r cube. In place of x you write r minus d. That's all. But as I said, it is common practice to express this in terms of surface value Gm by r square. So send one r inside the bracket. Becomes r minus d divided by r, that is 1 minus d by r. Therefore, gravity at a certain depth below the surface of a planet will be gravity on the surface into 1 minus d by r. And this formula is always applicable without any approximations or assumptions. So gravity at a certain depth from the surface of a planet is always given by this formula. And observe this formula as you go deeper into the planet. Means as depth increases, see depth is in the numerator, okay, but there is a minus sign before it. Okay, it's getting subtracted, 1 minus d by r. No? So as depth increases, gravity as a whole decreases. So from the surface, if you go deeper into a planet, gravity will decrease. And when d tends to, or when d is equal to capital R, if d is equal to capital R, d by r becomes 1, 1 minus 1 is 0. Gravity is 0. That means at the center of a planet, gravity is 0. Makes sense? Okay. You can treat the planet as a collection of shells. And the field created by any shell at its center is 0. Therefore, field created by all shells at the center also will be 0 only. That is why the gravity, acceleration due to gravity at the center of a planet is 0. Okay. And there's one more thing you can understand from all this, all the discussion that we have done till now. On the surface, it is Gm by r square. Okay. Above the surface, it is Gm by r plus h whole square. You know that as height increases, height is in the denominator, the whole thing, gravity, will decrease. As height increases, gravity decreases. So if you go outside a planet, gravity decreases. And we just discussed that if you go inside a planet, also gravity decreases. So where is gravity strongest? On the surface of a planet, gravity, acceleration due to gravity is strongest. As you go inside, it becomes weaker. As you go outside also, it becomes weaker. Okay. I think this much is enough about acceleration due to gravity of a planet. Next class, we will discuss something called escape velocity, how to make some object go away from a planet forever, never return. And we'll also talk about orbital velocity, how to make a satellite revolve around a planet in an orbit. So we'll be needing all these things there. Okay. Satellite revolves around the planet. So you need to know how much gravity acts on the satellite. And we'll be doing some energy based calculations also. You need to send the satellite to certain height above the planet. No, you have to supply energy to it. The rocket should, the rocket satellite system should be given sufficient energy to go there. So based on that, you can do fuel calculations and all. Then escape velocity, how to make something go away from the purpose of escape velocity is not actually to make something go away from a planet, but escape velocity, which is basically the velocity which is needed for an object to go away from a planet, will help you find out whether some object will come to a planet or not. Okay. Anyway, you'll understand this in detail in the next class. So make sure you revise whatever we discussed till now, and tomorrow you'll be given a worksheet, solve it. Okay. Thank you all. We'll continue in the next class.